So I shall stop sharing and we'll go here. So welcome everyone to our first Astronomy on Tap live stream. And it's also the first Astronomy on Tap of 2020. Unfortunately, we have to go online because of the current COVID situation. Sorry. So it's the first, unfortunately, because of the COVID situation, we have to move online, but we're all doing our part to, make sure we can stop the infection. So we're moving online, which is great. And the new year, it's a time of, beginnings and ends. You kind of think about the past year and having resolutions for this year. And we thought it'd be a great time to talk about the life cycle of stars, talk about the birth of stars and the death of stars, because stars are all throughout the universe and they're very important for how we kind of get a view into it. So today we have, myself, I'm Reggie, hi. We'll have Dr. Michael Küffmeier telling us about the birth of stars, and Dr. Charlotte Angus telling us about how they can go boom. And we have our helper, Jörgi, who will be looking at the live chat and trying to take down questions. So if you have questions throughout the talks, please put them in the live chat and we'll ask them to our speakers during question time. So we might get started. So to begin, we have Dr. Michael Küffmeier. He completed his PhD in Copenhagen, which is has connection here. Was doing a postdoctorate in Heidelberg, and then was recently awarded a Marie Curie, and is meant to be in the University of Virginia right now. But because of the pandemic, he is stuck in Copenhagen, which is great because we get to have you tell us about star formation. So, Michael, do you want to take it away?
The tale of the sun's birth. Once upon a time, in a galaxy called the Milky Way, there was a cloud of gas and dust. This cloud became so massive that it collapsed and formed thousands of stars. One of these stars was the sun. Shortly after the sun's birth, 8 planets formed around it: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. After this short period of formation, that means a few million years, the Sun, together with its planets, lived a relatively calm life for more than 10 billion years. Earth had a midlife crisis at the age of 4.567 billion years, struggling with humans who couldn't have their beers on tap, but the Sun didn't really bother about it. Eventually, the Sun evolved to a red giant and ended its life as a white dwarf. But that's another story. Instead, let's hear more about how the Sun and other stars came into existence.
Yeah, thank you, Julia. With this short story, I'm very happy to be the speaker here today and to be the first remote speaker for Astronomy on Tap quarantine edition. If you know it works. So cheers to all of you. And so it's basically, it's not Astronomy on Tap today, it's Astronomy on Can or Astronomy in a bottle or Astronomy on laptop, as whatever you want. And cheers. After hearing this nice story about the Sun and the origin of the Sun, let's try. I hope I can tell you a little bit more about some more details about this process from in a little bit of a different way. And as nicely introduced, so I'm unfortunately stuck in Copenhagen, which is actually not so bad because, I'm back in Copenhagen, except for the weather. It's a very nice place. So before we start, let's have one thing clear. We talk about stars and the birth and death of stars, but what is a star? So, well, according to the Oxford Learning Dictionary, a star is a large ball of burning gas in space that we see as a point of light in the sky at night. That is probably not so surprising to most of us. So if you look at the night sky, I guess, depending where you live, you see more stars when you're more living remotely. If you see less stars if you're closer to a city, but still a star, I guess every one of us seen it so far. And nevertheless, there's one thing that is quite important here in this definition. And the definition is the burning gas part. And that is really what is another way physicists might say this is fusion of hydrogen in the core of the star. But today what we'll actually talk about is kind of the sequence before how the star formed. So the objects I'm talking about today before the star forms, or when the star is forming, that is actually not necessarily visible by the naked eye. So please keep that in mind. And this also process is rather short, just a few million years compared to billions of years, the lifetime of the star. Okay, so let's go further into it. What about stars? How do they form? Where do they form? Well, they form in so-called molecular clouds. And these molecular clouds are typically 10 to 100 parsec in size. And that corresponds to about 2 to 20 million times the distance from the sun to the Earth. So it's quite large. And why are they called molecular clouds? Well, they're called molecular clouds because they consist of molecules. And these molecules, the reason why they are molecules has to do with actually a minor ingredient in these clouds, or in the interstellar medium in total, which is dust. And let me briefly go into that here with this little video that I'm showing you now. So 99% of the content is gas and 1% is dust. But the dust is important. So notice here, so we are now inside a molecular cloud. So you see the size scales here. So here is 2 light years. 2 light years, that's about half a parsec in a way. So that was in the context of the definition before. So we're well inside it. And now we are zooming in onto an individual dust grain. So we're moving further in. You have the dust grain. The dust grain is much, much smaller. It's 0.1 micrometer. So that's 10 million. So that's 1/10th of a million of a meter. So it's really small. Nevertheless, compared to the size of an atom, that is actually quite significantly large in comparison. So now we're on the dust grain, and you can see here these small balls that are moving around. The red balls are oxygen atoms. We don't care so much about them. What we really care about are these white balls. These are the hydrogen atoms. So what can happen is that these atoms, they can stick on the dust grain for a while and move around. So now we can see first, we see what happens here is like oxygen reacts with hydrogen, it reacts again with hydrogen, and it forms water. And the water sticks to the dust grain. So it is it's really like an ice layer that forms in this way on such dust grains, and it stays on it. However, now let's focus on the particle, the atom that was highlighted just before, that just came onto the dust grain, and you can see what happens with it now. It reacts with another atom on the surface, and you have now H2. However, now the evolution is different. What happens now is this H2 molecule is released, and it's released back into the gas. So now it's in the cloud again, and that's really the reason, the main formation site of these molecular clouds. So let's have a look at the entire video again without all the annoying interruptions here. So we are inside the molecular cloud. We are now zooming in onto an individual dust grain. So there are 1% of the content is made out of dust. Here are the different atoms, and oxygen and hydrogen, they react and become water, but that's forming an ice layer. But what's really happening here is, what's really important is the reaction of hydrogen with each other, and this is the mechanism of forming molecular hydrogen. That is the major constituent of molecular clouds. Okay, so we know that now. So this is really the birth side of stars, and to follow up a bit further, to see, look a little bit more into the entire sequence, let's have a look at this cartoon. So in the lower left and the upper left, you see a giant molecular cloud of gas and dust, like a cartoon of it. And now during the evolution, during millions of years, you start forming so-called filamentary structures in this molecular cloud. So there's compression going on, and the gas and dust becomes denser. Eventually it becomes so dense that there are these so-called dense cores that can form. And this is really the point when gravity really takes over, dominating everything. And note that dense cores are really important because they are really the birth site, they are really the progenitor of stars. And it's a bit of an odd name, because it's not really a core of a star. The core is larger, the dense core is larger than the star, but that's how astronomers are. We like to confuse people. So, but just keep it in mind here. So these dense cores, they form inside the filaments. So they are the cores in the filaments, but they are larger than the stars. And now it becomes gravitational unstable. So the mass is so massive and it starts to collapse. And voila, there you are, you have a star. So the star forms, and notice also that there is something else forming on the star, and that is the disk. And this disk forms because there's also a lot of rotation in the cloud and eventually in the core that is then producing this disk that consists of gas and dust. And why is this disk important? Well, this disk is important because the disk is the birth site of planets. And well, planets are important because we care about them, because we are living on a planet. And this is like really the overall cycle and circle. So to briefly summarize at this point, so stars and planets are really the smallest entity in a hierarchy of scales. So you have these large structures, these large molecular clouds, and then you go further down, and eventually you end up in this sequence with a star and a disk, eventually a planet. This becomes even more clear if we have a look here at this nice video by a collaborator of us, where you can see the formation, or like you can see the location of stars. So note the white dots are the stars, and the color coding that shows you the filaments. And I'm sorry here. So let's try again. So we can see that we now see that the stars are located in different locations here inside the cloud and along these filaments. Note also that there are no disks seen here. And the reason is just because of, this is for computational reasons, it's too expensive to model it here. And that's why they don't appear. But still, it's quite clear that you have these stars also kind of quite clustered to each other and being located in different environments and different parts here of this molecular cloud. This point, so we can see here, so really the molecular clouds are really an important part in the history of stars. At this point, you may think, well, I'm a little bit tired now of hearing so much about these molecular clouds and whatever. Tell me something more interesting and tell me more about stars. That's why I'm here. And okay, we'll do that, but I will do that with a famous or a popular approximation that we use to understand complicated problems, and that is a so-called spherical cow approach. And it really describes this. So imagine you have a cow. It's has a lot of asymmetries. And what you do is you just assume it's a sphere to approximate the problem, which makes it much simpler to understand it and to follow it. And that is the same what you also do in astronomy with molecular clouds or with the dense cores. So you know there are a lot of asymmetries. The problem is quite complicated, But we say it's, well, it's not, forget about it. Let's just say it's a sphere. So keep that in mind. So we're doing that now. And this leads us then, so this can be used then to get a very conceptual understanding of the formation of a star. So here to the upper left, we have what is labeled called here a pre-stellar core. And well, this is just another name for the dense core. So again, we like to confuse people, but the pre-stellar and dense core is really means the same thing. It depends a bit on your perspective. So modelers prefer pre-stellar core, the term pre-stellar, while observers prefer the name dense. However, then, well, done, never mind. So we are here at time 0, and you can see the size scales here are about 10,000 to a few 10,000 AU. So, and keep in mind, 1 AU is this distance from Sun to Earth, and that is roughly 150 billion kilometers. So it's quite a large construction here to begin with. Then it starts collapsing, and when it collapses, you start forming a star at the center, or actually a protostar in years. The sequence continues, and notice here that there's less and less material in the surrounding, so the so-called envelope, and there's like not much left of this remnant material. But notice here what's important is the inner part, this disk. So you can see there's rotation going on. And once again, so what's really, why is it rotating? Why is there the disk? It can really understood here in this cartoon, because you have the vertical component that cancel out each other. So look here, material is falling towards the star from the top and from the bottom. But so the vertical components, they cancel out each other. What you're left is the net rotation of the pre-stellar core. So this is happening then on timescales of about a few 100,000 years. And at the same time, you also start launching these outflows, which I won't go into detail. They're related to magnetic fields, but this is like beyond the scope of this talk. So we continue in our sequence, and we call it class 0, class 1, class 2, class 3. This is a way of distinguishing observations. And the star with its disk is less and less embedded, so more and more material is falling onto the star disk system, and we end up with an isolated disk. And in this disk, we are forming our planets, and eventually, on timescales of billions of years, we are left with systems such as the solar system, where you have the sun at the center and several planets around it that can live a wonderful life, more or less wonderful, for a few billion or several billion years. So this is really the overall picture that you have to keep in mind. So now a bit more about details. What's happening now is, well, the upper part is typically considered as part of star formation. So this is really what we historically consider as the topic of star formation. And then there used to be a kind of sharp transition for people working on disks and planets. And the reason for the sharp transition is that people really thought for a long time that planets start forming several million years after the formation of the star, so that the process of planet formation can be well approximated as being independent of the formation of the star. However, that picture has really changed in the last years, and by now it's really clear, in order to understand planet formation, we actually really need to understand the formation of a star. So planet formation starts already much earlier, probably already at this stage. So there's really some active research going on, which is why it's quite still a hot topic. Okay, but so what we want to ultimately do is, when we model things, so we don't want to start with a sphere, we don't want to start with a collapsing sphere, we want to start from an actual molecular cloud, larger scales, and you can see a video here where we have we do that, where you see these filamentary structures, and we zoom in onto an individual star with its disk. So here you can notice these filamentary structures, and they're the redder part that corresponds to higher density, and hence to location here eventually of the star with its disk here, where we are approaching, which we are approaching now. So this is really, really nice. So we can really cover this large range of scales in one simulation and don't need to make approximations on the initial conditions. A closer view here in 3D of this disk, you can see it here. This is a resolution for about 100 years, and you can see how the disk evolves, how the disk moves around, the star is at the center, and there's a lot of stuff going on. And this is really interesting because this is already the site when planets start to form. Okay, now you might say, I can tell you a lot. These are just simulations, fine, but what about observations? Here you go. These are really the observations of disks associated with young stars. And we notice the zoo. This is really remarkable. These are observations that are from I think 3 years ago or so, done with the Atacama Large Millimeter Array, a big telescope, actually multiple telescopes working together in the Atacama Desert in Chile. And then you obtain these wonderful images where you can see these disks with a lot of structure and noticeably a lot of rings and gaps in it. And this is really the reason also why we now strongly think that planets start forming much earlier, because that was quite a surprise that there are so many, that there's so much structure in these disks already, even though they're rather young. Also like to go a little bit, let me go a little bit further into, dive a little bit further into the disk part here. This is these are even more disks. So we have the zoo here slightly observed with a different technique. And let's focus on the upper left here, these upper left 2 disks. Here we can see them again. And what you see is these are so-called shadows. So you can see here is some light where the light is scattered. So the star is really at the center and the light is illuminating the outer part, but here these parts are in the shadow, and the shadow actually comes from a small disk, or most likely from a small disk that is located around this inner star. Also, slightly possibly related here, we have a system of a binary where you have 2 disks that are misaligned to each other, and yet another overall disk that has yet another orientation. And the question really is, how do such systems come into play? What is their origin? And so one thing that we are currently working on is looking at infall of gas and dust with different angles. So whether that could possibly be an explanation for it. And just to show you something for a recent simulation here. So this is based on a simulation where we have a disk and then some gas is approaching. And indeed, what you can see is that the gas is falling on, it's set up in such a way that it falls in with a different inclination, and you end up with a system where you have inner disk and an outer disk with 60-degree misalignment here in this case. And indeed, what we show by using so-called mock observations, you can see that the inner disk casts a shadow on the outer disk, which is very much in agreement with observations. So this is really, really nice. But so much about this detour. The talk is more about star formation. So let me summarize the talk and also come back a little bit more to the tale that we heard at the beginning, to really keep it in mind and to take away the main point. So we've been thinking of these diffuse clouds and molecular clouds of gas and dust. They evolve and we form dense cores within them. These dense cores are important because they are really the gravitationally collapsing entities that then form the star. And when the star is forming, it's not just the stars, and then it's just not just the star that is forming, it's also a disk that's forming around it. And this disk forms because there is rotation to begin with, and this rotation is, so the disk is really the result of this net rotation that is conserved. Then the disks are important because, well, the disks are the birthplace of planets, and this is for us of really existential importance. And now note that this is just, these are timescales of about millions, and we're talking about millions of years, which is obviously very, very long for human timescales. However, on the timescale of a star, this is really just a tiny fraction, because the sun, as we mentioned earlier, the sun in fact evolves for billions of years. So actually the age of the solar system is supposed to be 4.567 years, and 4.567 billion years, while we are thinking that we are roughly halfway through the evolution of our sun. And eventually our sun will also lose its mass again, and there will be also material going back into the clouds eventually again. So there's really really like a circle. But we will hear much more about the evolution, maybe of slightly different stars than solar mass stars. I think we'll hear more about more massive stars. But with that, I want to say thank you for your attention, and cheers.
My audio. Thank you, Michael. That was very fun to learn about, I guess, the birth of stars and planets. Yogi, do we have any questions from the stream?
Yeah, we have. If you can hear me, hopefully, we have only one question. I think. Oh no, now we have two. Okay, so the first question is that. Okay, now we have a lot of questions. Okay, so the first question is from Antoine Richard, and as he stated, he has always wondered about the rotation disks forming around the stars, and specifically, why is it a disk and not a sphere?
Yeah, so it's really a disk because so I'm going to move a little bit around. Yeah. So it's really a disk because of the cancellation of the vertical component. So you have the collapse, and sure, if there was no rotation at all, if it was like just static, so there wouldn't be any velocity inside the core, everything would just collapse towards the point mass, and you would just end up with something massive here. However, because you have some rotation in the core, this rotation is conserved. This is something called angular momentum conservation. And you can see here the vertical components, they cancel out each other. So you have material falling from the top and material falling from the bottom in this cartoon. That cancels out each other, while the component in the horizontal direction here is conserved and remains there. So this is really the reason why you have a disk.
Could I maybe chime in there if that was that might be a bit complex. It was still good. But the way I like to explain this is you might see in like videos of basketballers spinning basketballs really quickly on their finger, and if it spins faster and faster, it just starts to flatten out. You can also do the same thing with like pizza dough. You know, it starts out as a lump, but then as you toss it and spin it, it flattens out. So it's the same thing that sort of happened with gas. It just, because of this angular momentum, wants to flatten out into a disk. Is that okay? Yogi, do we have any more questions?
Yes, we have. So far we have 3 more questions. Yeah. So the second one is it's a bit a compound question. So I'm trying it's actually not really about your talk. It's more about cosmology. So the question is, are there any parts of space where we can find more stellar density of stars per space and galaxies, and how and whether it is related to the how it was before star formation, like on the universe scale, like before there were any galaxies and stars in the universe. Was the matter there distributed evenly or not evenly? And is the second statement true? Is the first statement true? And whether they are related?
That's it's a very long question. So let's say, yeah. So in order to form stars, you need to have material. So the stars do not form immediately after the formation of the universe. So there's the Big Bang and the universe expands, and you need to form, as we showed earlier here, the stars need to form from molecular material. So you need to form these molecules, to form this first. Does this make sense?
Mm-hmm. Okay. Yeah, but I think the question, as far as I understood the question, it was more about. So I'm not a physicist, but I presume the question is somehow about quantum fluctuations in the early universe and all that stuff.
Okay.
Maybe, yeah, you can a bit comment on that, like somehow.
Yeah, I'm not sure. I mean, I could say something, but there's I might risk that I'm making a fool out of myself. So this is really not my expertise here. So I'm a little bit. So what I'm not fully sure whether I fully understood the question. I must admit.
Yeah.
So I guess I'm on the chat now. I guess maybe if we just take the third line. You can probably answer this one, which is, are there areas in space where it might be more likely to form stars than in other areas?
Yeah, sure. So you have more. So you have more in areas where you have more material. So where you have higher densities, it's more likely that you form the stars. I mean, the thing is, maybe I should try to read the question. That would be helpful. I can't.
This is a question from Eleonora.
No, that's okay. We can go on to the next question. I think you answered the question about where stars form. You need to have gas. So we can go to the next question, which is, yes, this is an interesting one. What is the temperature evolution from first molecular arrangements into the configuration of a star? So my understanding is like, what is the range of temperatures that is gone through when you start off with the first molecules that form a star to actually having a star? I think that's what the question is.
Yeah. So the material here is when we form the star, the material is very cold. So stars are formed from very cold gas. It has to be cold because it's very dense.
How cold is cold?
Yeah, right. How cold is cold? So we're talking about minus 260 degrees Celsius. So 10 Kelvin. So it's really, really cold. This is then the material that then collapses, and eventually really are the smaller scales of the star. When so as long as a star, like a protostar, can radiate its energy away, it will stay cool. But really at smaller densities, at smaller scales, at high densities, as in this picture, really here on this scale, you heat up the star and you reach temperatures of thousands of Kelvin. So yeah, also thousands of degrees Celsius.
That is, yes, a wide temperature range, and I hope that answers the question about the temperature evolution. Interesting question. We have another question from Satna, but I don't know if you can answer this one. Okay, so is everything spinning because the star is dragging space-time around it, just like a black hole?
No, so the star is not massive enough to, a black hole is really has really a substantial effect on space-time. But these stars, the masses are quite relatively low compared to a black hole. So this is really you could just explain this. You could understand most of star formation actually just without knowing general relativity.
Interesting. I guess, Jörgi, do you want to ask the next question?
Yeah, sure. So the next question is from Nina Hakala. I hope I pronounced it right. And yeah, the question is, could we then conclude from all this that we are all made of stardust?
Yeah, that is, yeah, sure, that can be a conclusion. Yeah, that is the famous phrase. Is it from Neil deGrasse Tyson, or is it actually is it Sagan? I think Carl Sagan was the one who.
I know Moby has a song about that as well.
Yeah, I think Carl Sagan. I think this is the famous phrase of Carl Sagan in the Cosmos series, right?
Probably.
Yeah, actually, yeah, but that's that it's fair to say, because stars are important also for the content of the universe of materials. So they enrich it also with different molecules. And, we will probably also hear more about that in the next talk, especially as supernovae are particularly important to enrich the universe with molecules.
And so the next question you have is from Stefano, and Stefano asks, what mechanisms determine the plane of rotation of the dense core, and what defines the up and down in the step from class 0 to class 1 young stellar objects? I think that's.
So what defines one? Could you just repeat? That was a bit.
What mechanism determine the plane of rotation of the dense core, and what defines the up and down in the steps in the class 0 and 1?
I see. Okay, yeah. So it's generally quite random. So there's a lot of motion in this large molecular cloud. So there's so-called turbulence, and so it's very chaotic. But when these denser cores form, they will also have the gas will moving around in different orientations, but yet there is a net component. So overall, if you sum it up, there is one dominating direction of rotation, and that is then determining your disk plane. I hope that helps to answer the questions. And then so it's really consider like parcels of gas in such a core, and they move around, and then overall they have like one orientation that is dominating.
Yep, and so far at least, the last question you have is from Joachim, and the question is, how do you measure and how do you model processes that last millions of years when your observations only take a few weeks, months, or years?
Yeah, very good question. So yeah, we can do that, of course, in a model. That's the nice thing. That's also the reason why we can do models. So modeling is also a little bit like doing experiments. So in regular physics, like in smaller scale physics, you can set up an experiment and you can test things. However, in astrophysics, that's a bit tricky because the timescales are so large, as raised by Joachim in the question. So you have millions of years of evolution, and that's obviously impossible to follow up observationally. So you can set up models, and you can play a little bit. You can play God in a way. So you can really set up your universe. You can set up whatever, of course, with simplifications. But this is a way of following up longer timescales. To compare it with observations, in observations, what you can do is you look at different objects. You're limited in time, but you're not limited in the objects you're looking at. So since the universe is so big and so large, you can just look at very different objects, and afterwards you try to classify it. And from that, you can get an idea of how long a process lasts. So for instance, here in this, if we stick to this cartoon here, you can derive these timescales because you have a sample of observations, and then you can see that, for example, these class 0 cases, they are way less there's very less frequently that you observe this type of objects than you observe class 2 objects. So this is really how you get an idea of the timescales.
Neat. We currently don't have any more questions on the live chat, but more might come through. I have some questions, I guess, for you, Michael. So what drove you to, I guess, research star formation? Like, how did you get into this?
Yeah, so I don't think it's like can't tell you the classical story that I knew about this like since I was born, but so I was interested in school I was interested in how stars form, about the universe, about the origin of the solar system to some extent, and then but then I was also interested in other things and started physics and started studying physics, and during my third year, then I got a little bit more into astrophysics. I did a course there, and then thought like, okay, this is actually not so bad to do, and I liked it. And then it was really going into star formation in particular was really a bit by chance as well, because then I was curious about planet formation, and I was asking of potentially doing a master thesis on something related to planets. And then I talked to my supervisor, and he had a project in mind, and I was just about to ask for a few minutes, and then I left the office 1.5 hours later after he had told me about all his grand ideas, which would have been, which was supposed to be done within a couple of months, and well, that was several years ago, and I'm still doing it. So this is kind of the story.
So research is never ending, I guess. So someone asked a question about, I guess we're all made of stardust, which I guess makes me think, how does, and maybe the audience also want to know, how does, I guess, stars and the types of stars that we get change over the age of the universe? So I guess we're all made of stardust. We have carbon and silicon and stuff that had to be made in stars. But then what came before those stars, and what came before those stars? Like how is the stars in the universe evolving?
Yeah, so you have more and more. You have the production of more and more metallicity, so to speak. So you have more and more enrichment, and so the content of stars changes. So really, at the earliest stars are basically so-called metal-free, and then it's metal-free means that they are metal in astronomical terms is that there's nothing more, that the elements is really elements are really limited, so there's not much heavier elements than hydrogen and helium. So that's changing during the age of the universe. So because you have this life cycle of stars, you have more and more production of heavier elements, for example through like stars as the sun. They evolve towards red giants, and then they can produce elements up to carbon and oxygen. But and then some of these elements may then actually be released to the universe, back into the universe. But heavier stars, like can actually evolve to supernovae, and then they really make boom. And these are really exciting places in the universe where you can produce these heavier molecules, heavier atoms, heavier elements, and so over the time there's more enrichment.
So I guess we've filled in your allotted time, so we'll thank Michael again if you're just clapping from home. Thank you for teaching us about star formation. We might take a little 10-minute break before we go into our next talk. So we hope that you enjoyed that. So we will resume at 10 to 8. Oh, and by the way, if you are enjoying Astronomy on Tap, maybe you would feel like donating to us. So this is all completely volunteer run by researchers in Copenhagen, but we do have to advertise events and get the administrative tools and hopefully pay off our graphics person. So if you are enjoying this, maybe you can do that. So I will share this. So here we go. So this is the mobile pay if you feel like donating to us. And also our next event is on February 3rd. Because of the restrictions, it's meant to be in person, but we'll see how things go. So that event is now available and you can sign up for it. We've actually moved venues. We're in a much bigger venue now to hopefully accommodate everyone. So if you are keen, we'll be talking about blazing binaries, because next month celebrates 5 years since the discovery, or since the announcement of the discovery of gravitational waves. So we thought we'd talk about gravitational waves and stars colliding. So enjoy your break, and we will resume at 10 to 8. Everyone. So we hope that you had a nice little break. So we will move on. Sorry, I'll put my video back on. Hope that you had a nice little break. So I guess we'll move on to the next talk. Charlotte, are you available? Yes. There we go. So in the first talk, this month's theme is Birth to Boom, and we learned about the birth of stars. And there's like this bit in the middle we're currently living in it, and apparently stars don't really do too much until they come to the end of their lives. So Charlotte completed all her studies in the UK, I took notes, in Sheffield, and then went down to work in Southampton, and is now a postdoc at Dark Cosmology? Yes.
Yeah, that's right.
Yes. And likes to look at how things go boom. And she will educate us on that. So would you like to take it away?
Sure. Okay, let me just share my screen. Come on. Sorry, 1 second.
It's all good.
Okay. Hopefully everybody can see this. Okay, so thank you very much, Reggie, for the introduction. We've heard a lot about how stars are formed at the beginning of this evening. So I'm now going to take you to the other end of the spectrum, and we're going to have a look at how stars can end their lives, and namely the explosions that can occur at the end of a star's life that we know as supernovae. So if you were to go out and look up at the night sky, probably not tonight, probably not in the middle of Copenhagen either. There's far too much light pollution going on in the middle of a city. But if you were to go out somewhere, say in the middle of the countryside, and when it's exceptionally dark, look up at the night sky. If you're really, really lucky, you might see hundreds and even thousands of stars. And perhaps you might be able to see this dusty band of light that marks the plane of our galaxy, the Milky Way. But if you were to go out the next night at roughly the same time, or the night after that, or the night after that, you might think, my universe is actually kind of boring. It doesn't really seem to be changing. There doesn't seem to be a lot going on. I mean, sure, it's pretty, but nothing happening. That's not necessarily true. So if your eyes were just a little bit more sensitive, and when I say a little bit more sensitive, I mean they were, say, 0.5 meter, maybe a little bit larger across. Might be quite hard to get glasses that fit. But if your eyes were just a little bit more sensitive, you might start to see new points of light appearing all over the night sky at a rate of roughly 1 every 30 seconds. Each of these new points of light marks what we call a transient event. This is something in the universe which is varying in brightness over time. And if your eyes were super, super sensitive, and by that I mean about 8 meters across, which is the size of these large research telescopes shown in this image here that are in Chile, the night sky would seem to be alight with varying sources of light. Now, some of these sources of light are what we know as supernovae. These are the explosions that mark the end of a star's life. But how exactly do you make a star explode, and how many ways can you do that? Well, it all kind of boils down to how big your star was in the first place. So let's start with the little stars. Let's look at low mass stars. So throughout the majority of a star's life, it produces energy through a process that we call nuclear fusion. So nuclear fusion is basically taking 2 small particles, 2 small atoms, and throwing them together with lots and lots of speed. And when you throw them together with lots and lots of speed, they stick together and they form a larger particle. And in the process, they release a little bit of energy. They release lots of other crap as well, but it's the energy that we're focused on, because that little bit of energy starts to heat up the middle of the star. It gives the gas within inside the star thermal energy, and this thermal energy means that the particles of gas in the star have random motion. And this random motion exerts an outward pressure. Now, stars are quite big things. They've got a lot of weight to them, a lot of mass. And all that mass wants to collapse in on itself. It wants to compress under its own gravity. But the outward pressure from the thermal motion of the star stops it doing that. So throughout the majority of a star's life, it's kind of in balance. It's balancing its gravitational pull with its outward thermal pressure. And all the while, it's generating energy in its core through the process of nuclear fusion. So stars start off generally as balls of roughly hydrogen gas, and that hydrogen fuses to form helium. And then eventually in a star, it might get hot enough for the helium to start fusing to form things like carbon and oxygen. Now, in a low mass star, and when I say a low mass star, I mean a star that's less than about 8 times the mass of the sun, which seems quite big, but is actually quite common and fairly low mass as far as stars go. You can get hot enough to fuse your helium into carbon and oxygen, but in the core of the star, it never really gets hot enough to bash your carbon and oxygen particles together to fuse them into anything heavier. And because of this, the carbon and oxygen doesn't really do anything in a low mass star. So over time, you have these like shells of material, you have these shells of helium and hydrogen material surrounding a growing carbon and oxygen core. And you've got enough fusion going on in these shells of material to keep your star afloat, to stop it collapsing under its own gravity. And that's all great. But eventually, that's not enough. So at the end of a low mass star's life, once its nuclear fusion in the shells is kind of running out, it starts to blow away its outer layers of material in these big dynamic stellar winds. And what you're left with is your carbon and oxygen core that you've been building up over several billions of years, surrounded by these huge bubbles of material from the outer layers of the star. Now, these huge bubbles of material are really, really pretty to look at. They're called planetary nebulae. And if you have 5 minutes or you want to waste an hour, because I could spend an hour looking at these things, I recommend you Google them because we've got lots and lots of them in our galaxy and they're incredibly pretty to look at. But what we're concerned with tonight is that carbon and oxygen core that's left behind. Now, that carbon and oxygen core, as we said before, it's not doing anything. It's not hot enough to start fusing by itself. So it's not producing any energy. And the problem with this is that because it's not producing any energy, there's no heat to create thermal motion for the carbon and oxygen in this core. And therefore you experience this drop in thermal pressure. And that means that you have an imbalance of forces and your gravitational attraction begins to win. That means that this carbon and oxygen core begins to collapse under its own gravity. Now, in a normal gas, your particles can kind of fly about all over the place and they have random thermal motion. However, we're taking away this energy from the particles and we're beginning to compress them together. And as we begin to compress the gas together, you start squashing the particles into a much more confined space. So there's absolutely no social distancing going on here at all between these particles. But you do reach a point with the carbon and oxygen core at which the collapse stops. And it's due to a principle of quantum mechanics called the Powly exclusion principle. Now, to not go into too much detail, the Powly exclusion principle basically says that no two electrons can occupy the same orbital between atoms, which means that you can only squash your particles so close together. I like to liken this to getting on a really busy like metro or bus and it being really, really packed and there's standing room only. In order to give yourself that little bit of personal space, you start kind of like wiggling your elbows out a little bit. And it's that little bit of outward pressure that stops the star from collapsing. This pressure is what we call electron degeneracy pressure. And once you have a big ball of carbon and oxygen rich material that's supported against its own gravity from electron degeneracy pressure, what you've created is what in astronomy we like to call a white dwarf. Now, a white dwarf is something that's approximately the mass of the sun that's been squashed down into something the size of the Earth. Now, something the mass of the sun that's been squashed down to the size of the Earth is insanely dense. So if I was to take my extremely strong extragalactic teaspoon, patent pending, and take a scoop off the top of your white dwarf, the mass of the material contained on that teaspoon would weigh approximately 5 metric tons, or roughly one fully grown African bull elephant. Sounds great, but not really something I want to stir into my cup of tea. Now, white dwarfs themselves are like fairly stable, but they're only stable to their own gravitational pull as long as they stay above a magical limit that we know as the Chandrasaka mass. Now, the Chandrasaka limit. Now, the Chandrasaka limit means that any object supported against its own gravity through electron degeneracy pressure is only stable as long as its mass lies below 1.4 times the mass of the sun. I say 1.4, it's approximately 1.4. There are certain conditions, such as if you give your white dwarf a little bit of spin, or you give it a magnetic field, or you tweak the circumstances slightly, where you can move this limit down or up a little bit. But on average, it's about 1.4 times the mass of the sun. Below this mass limit, your white dwarf is stable. But what happens when you push your white dwarf above this mass limit? Well, firstly, we've got to find a way to add extra mass, because this white dwarf is just kind of sitting out there in the universe. It's not really doing anything. But the universe is really, really kind, because the universe likes to make stars in pairs, stars like friends. The majority of stars are born in what we call binary systems. This is where you have two stars that are orbiting a common center of mass. Now, if you were to make one of those stars a white dwarf, and you were to make the other one just a normal star, and you were to make them a little bit closer, you push that orbit in, you put them in a really, really close, really, really tight orbit, your white dwarf is insanely dense. And because you have a really dense object, it has a really strong gravitational field. And when you've got an object with a really strong gravitational field in a close binary system, you can begin to distort the gravitational potential of your other star. And when you do this, you can draw or steal material from the pair star in the binary system. When this material is drawn away from the pair star, it begins to fall into the white dwarf in a process that we know as accretion. And once this material falls onto the surface of the white dwarf, it fuses and burns and starts to slowly increase the mass of your white dwarf. So that's one very neat way to start pushing your white dwarf up towards that magical Chandrasaka limit. Another slightly less neat way to do it is to just bash two of them together. So if you have two white dwarfs in a binary, you've got two very, very dense objects, which have two very, very strong gravitational fields that are orbiting around a common center of mass. Now, two dense objects, or two objects orbiting in a binary like this the binary system will lose energy over time. And that's because you're rotating your gravitational field, which means that you start to lose energy through gravitational radiation. And when you do this, as your binary system starts to lose energy, the two white dwarfs will begin to spiral in towards each other over time. And over time, they will get closer and closer together to the point where they actually collide and merge and hopefully form some mass of carbon and oxygen-rich degenerate material, which is above your Chandrasaka limit. And once you push your white dwarf above this Chandrasaka limit, you generate a thermonuclear explosion. And that's because the minute your white dwarf goes above this limit, it's suddenly no longer able to support itself against its own gravitational pull again, and it begins to collapse in on itself, and it triggers rapid nuclear fusion. And once you start triggering this rapid nuclear fusion, you start creating more heat. And as your burning material starts to heat up, you trigger more reactions, which creates more heat. And you end up in what we call a runaway thermonuclear explosion, which burns through all of the material in your carbon and oxygen-rich white dwarf within just a matter of seconds. And it creates this really, really luminous explosion. And it's this explosion that we see as what we call a type 1a supernova. Now, type 1a supernovae are exceptionally luminous. They're so luminous that they've been known to outshine entire galaxies. And to just give you an idea of how easy they are to spot, this is the galaxy in which one went off around 10 years ago. You might recognize it. It's called the Whirlpool Galaxy, or M101. And on the left here, I'm showing an image of the galaxy taken before the supernova went off. And on the right, I'm showing an image of the galaxy when the supernova went off in 2011. And you can see there's this whole bright new point source of light that's easily identified in the images, outshining the entire region around it. And just to give you an idea how bright these events are. Now, if you're an astronomer like me, you like to track how transient events evolve over time. And we do this by mapping how bright the transient appears to us over time. And when we plot this, we call it a light curve. Now, light curves have two key features. There's the peak of the light curve, which is the maximum brightness that your transient attains. This peak brightness is normally driven by the amount of radioactive material you generate during the explosion. So in the case of your white dwarf, it's the amount of radioactive material you generate during that rapid thermonuclear burning. And the peak is normally driven by the amount of a particular isotope called nickel-56 that you produce during the explosion. And likewise, we're interested in how slowly or quickly the transient fades from our sight. This is called the decline. And the decline is normally driven, again, by the amount of radioactive material that you produce during the explosion. But the rate of the decline is determined by the radioactive decay of the materials that you produce. In particular, the radioactive decay of nickel-56 into cobalt and then into iron. So the really cool thing about Type 1a supernovae is that you're always blowing up roughly the same amount of material every time you see one. You've always got roughly 1.4 solar masses of carbon and oxygen rich electron degenerate material undergoing a thermonuclear explosion. And because of this, the light curves of Type 1a supernovae are basically all the same. I've caveated that there because there's a little bit of wiggle room. You can get some that are a little bit brighter, some that are a little bit fainter, some that are a little bit faster, but you can correct for that. And because all of these light curves are essentially the same, what you effectively have are what we call standard candles, or what I like to call cosmic light bulbs. So when you take a light bulb will give you a certain amount of energy when you turn it on. If you were to look at that light bulb, you know intrinsically how bright that light bulb is when it's a very close distance to you. So if you were to look at that same light bulb giving out the same amount of energy, but much further away, you can work out, based on how bright that light bulb appears to you, how far away it is. And what you've effectively created is a cosmic ruler, a way of measuring distances across the universe. We do this with Type 1a supernovae. We know how bright they should be, and therefore when I see one, I can tell you, based on how bright it appears to me, how far away the galaxy it went off in is. And this is exactly what astronomers have done. Using Type 1a supernovae, we've been able to not only measure the distances to very distant galaxies, we've been able to look back in cosmic time and work out, based on how far away these Type 1a supernovae appear to be to us, exactly how the fate of our universe is evolving. We've been able to use Type 1a supernovae to discriminate against different cosmological models of how our universe is evolving. And we've been able to show that not only is our universe expanding, it's accelerating in its expansion, which I think, given that this all comes from like the itty bitty remains of a tiny star, is really, really cool. Okay, so I've talked a lot about low mass stars. Let's have a look at what goes on at the higher mass end in stars bigger than about 8 times the mass of the sun. So much like in a low mass star, high mass stars generate their energy through the process of nuclear fusion. Only once they get to the carbon and oxygen stage, like in a lower mass star, their cores are actually hot enough that they can continue fusing that material. And they can fuse through carbon, through oxygen, to neon, to magnesium, to silicon. So if you were to take a really big knife and take a big slice through a massive star, you would actually see a very onion-like structure within the star, with layers of progressively heavier elements as you move towards the center. And you can actually continue fusing all the way down to iron. And we start to build up iron in the core of your star. However, iron fusion is really, really tricky. And it's because of this little complicated graph here, which I'm hopefully going to try and explain for you guys. So this chart here is looking at all of the elements in the periodic table ordered by the number of protons on the x-axis that are present in the nucleus of the atom. So you're looking at increasingly heavy elements on the x-axis. On the y-axis, we're looking at what we call the binding energy per nucleon. This is basically a measure of the amount of energy it would take to completely tear apart all the constituent parts of the nucleus of that particular the element in the nucleus of that particular element. So it's basically a measure of how stable that particular chemical element is. So we can see at the very low, at the very early atomic numbers, so in your lower mass elements, as we move along the periodic table, we see a general increase in the binding energy per nucleon. This binding energy per nucleon is also a reflection of the amount of energy that you get out during nuclear fusion. So when you take 2 lighter elements and you bash them together and you form a slightly heavier element, the amount of energy that's released is proportional to the binding energy per nucleon for that particular element. So this is all kosher up until iron. When we reach iron, iron is at a peak. Iron is a fairly stable element. And then for elements heavier than iron, the binding energy per nucleon is less than the binding energy per nucleon for iron. And this means that you have to put more energy into the fusion reaction. You've got to give your particles more energy in the first place than you get out of the fusion reaction when you make an element heavier than iron. And this means that the fusion of iron just naturally doesn't happen within the universe. Well, at least it doesn't happen very often at all, because it's not energetically favorable. So therefore, what happens in the core of your star is you're fusing all of these different chemical elements, which are eventually adding more and more iron to the core. But the iron isn't doing anything. It's just coasting along. It's sat in the middle of your star. It's getting heavier, and it's not contributing to the welfare of your star at all. It's just adding extra mass. And eventually, that iron core isn't going to be stable to its own gravitational attraction. And at that point, when the iron core begins to collapse, even electron degeneracy pressure, like we saw with the carbon and oxygen core that eventually forms a white dwarf, that pressure isn't enough to support the amount of material that wants to collapse, the gravitational pull of all of that material collapsing in on itself. So once you reach that point, you actually push past that and you start to force the electrons inside their parent atoms. And when you force the electrons inside their parent atoms, you combine the electrons with the protons and you form lots and lots of neutron-rich material. And this continues collapsing down until you just have this really dense ball of neutrons. And at that point, for most stars, the collapse will stop because the neutrons themselves exert what we call a neutron degeneracy pressure, which is similar to the electron degeneracy pressure, but not quite. And it's that slight outward force again, which halts the collapse. So what you end up with is a really dense neutron-rich core. And this newly formed neutron-rich core is something, again, about the mass of the sun, but squashed down to something around 10 kilometers across, so something the size of Copenhagen, something you could cycle around if you were feeling energetic. If you were to, once again, take your extragalactic teaspoon and take a scoop off the top, the amount of material on that teaspoon would have a mass of around 1 billion tons, or around 900 times all of the pyramids of Egypt combined. So whilst this is all going, this collapse of your iron core all occurs within less than a second. And what's happening to the rest of your star? Well, it's a little bit like when you have a character in a cartoon who's running along the top of a cliff, and they run over the edge of the cliff. And for a second or so, they carry on running until they look down and they realize, oh no, there's no ground underneath me. And then they plummet to the earth. It's a little bit like that with the outer layers of the star. They kind of carry on fusing for a few seconds after this has all happened, and they haven't quite realized what's going on. And then suddenly they effectively look down and realize that there's been a sudden drop in pressure in the core, and they all begin to cascade downwards. So you have these layers of successively heavier elements all falling down on top of one another, all falling towards this newly formed, really, really dense, really, really hard surface. And what happens is, as they collide with this hard surface, they rebound outwards. And it's this rebounding material that we see as a shock explosion that we call a core collapse supernova. Yeah, there we go. So in a core collapse supernova, you've got this rebounding material outwards, and you're suddenly given all of these layers of material, all of the particles within the outer layers of your star, lots and lots of energy. And because you're giving them all this additional energy, and as they rebound outwards, they start to collide with each other. These layers of material start to collide with each other. And when you've got really energetic particles colliding with each other, guess what? You get more nuclear fusion, which means that you are able suddenly to fuse those heavier elements heavier than iron in this shock rebound. And it's this way that we can generate some of the more heavy elements in the periodic table. Come on, there we go. So what you're left with is your little neutron-rich core, which we now call a neutron star, sitting in these massive blown-out shells of material that we call a supernova remnant, where you've got lots and lots of newly formed chemical elements. Again, if you've got an hour spare, you want to go look at some pretty pictures, I recommend you go and look at images of supernova remnants. There are some really fantastic ones out there. And just to kind of highlight this, like how much these supernovae contribute to the chemical enrichment of the universe. This is a periodic table of all of the different elements broken down by their rough extragalactic origins. So everything that's highlighted in orange comes from a core collapse supernova, is either fused within the core of a massive star or is generated during the supernova explosion as all of that material rebounds outwards and begins to energetically collide with each other. And I think this is really cool because it's actually like the kind of composition of us is a roughly 73%, I think, composed of elements that are formed within either massive stars or core collapse supernovae. So as I think we had a question earlier, we are mostly stardust, which I think is really, really cool. Okay, so I've given you a couple of very general scenarios for how supernovae occur. Is that it? Is that really the end of the story, Charlotte? No, it's not. I can literally hear you all sigh like, oh, come on, finish talking. I'll not be long. Okay, so astronomers we've seen a revolution in transient astronomy over the last 10 years. And this is basically because astronomers like myself we've designed these surveys using very large telescopes where we go and we scan large regions of the sky night after night after night. And we do this so that we can all play a giant game of spot the difference. And what we do is we take new images every night of the same patch of sky. And when we do this, we can take away old images away from the new images to see if we can see new point sources of light appearing and therefore identify new transients. And it's a very, very efficient way to do it. And because we've changed the way we search for transients rather than just going, oh, there's something new up there, we've been able to identify a whole, an entire zoo of different kinds of transients. So this is a very fancy chart, which basically maps all different kinds of transients in terms of how bright they get at peak brightness against how long it takes them to decline. So it's those two key features of your light curve. And to just put this in context, the deaths of low mass stars, the type 1a supernovae, they occupy a really small region of this parameter space. Now, partly that is due to the kind of physics of what's going on, but with core collapse supernovae, they still don't occupy they only occupy a very contained region of this parameter space. It's a bit bigger because you've got a slightly wider range of setups. You can have a slightly bigger range of stellar masses undergoing collapse, but it's not the entire picture. There's so many different weird and wonderful transients out there. And it's the job of myself and others working at DARC and collaborators all over the world to try and both identify new types of transients, but also work out what the heck is going on with all of these weird and wonderful explosions and try and work out how those connect to stellar evolution and stellar deaths. Okay, I think I've whittled on for long enough. Thank you very much for listening.
Thank you, Charlotte. So yes, if anyone has any questions, please add them to the live chat. There is a slight delay between when we talk and when people hear what we talk, so hopefully there'll be some questions popping up soon. But I guess in the meantime, I have some questions, and hopefully other people were thinking this question as well. Everyone loves black holes, and I know that some really massive stars can become black holes, but how big do they have to be?
So how big does the star have to be?
Yeah, I guess how big does a star have to be to become a black? And I guess you can talk about the process of how does it become a black hole?
Okay, so in order to create a black hole at the center of your star, basically to push past that neutron star phase, to push against the neutron degeneracy pressure that kind of halts the collapse in some more massive stars, you need to have a bigger iron core to begin with. So what happens is basically your iron core is, again, once it forms a neutron star, that's still too heavy. It cannot support itself against its own gravitational pull, and it will then collapse down into a singularity and form what we call a stellar mass black hole. In order to do that, you need to have a star that's roughly bigger than about 40 solar masses, so 40 times the mass of the sun to begin with, in order to form an iron core that's dense, that's heavy enough that it can no longer support itself once it reaches the neutron star stage.
And are stars that massive rare?
Yeah, they're pretty rare.
Okay, yeah. So there's no risk of our sun turning into a black hole.
Absolutely no risk.
No, that's okay. Still waiting on some questions to come through. I still have some more questions. So I was really surprised at the frequency. So once every 30 seconds, a star is going supernova, I guess. And do you feel sad about some of the ones that we don't catch, or because of these surveys, you think that we're okay with getting most of them?
So I think in principle, it hurts me a lot that I can't tell you exactly, how many supernovae are occurring at any one time because I can't see them all. It is a trade-off. So unfortunately, with surveys, you're always going to miss some level because some will be too far away, so you can't quite see them because your images don't go quite deep enough. Or some of them you don't actually look at the right area of sky at that time of night. And it's always a trade-off in a survey. You either look for a very long time at a much smaller region of sky, and therefore you're kind of looking for a bigger volume, and you will see more supernovae that way, or you will be looking at a wider area but not quite as deep. And that's always a trade-off with modern astronomical surveys. It hurts me, but also you kind of have to appreciate you can't do, unless you have, multiple telescopes everywhere, which I think is the thing we should try and crowdfund. No? You can't always do that.
There are some questions now.
Yep.
And so the first question is from Magic Space Monkey, who loved the talk. And the question is, what mass is required for kilo and hypernova? Sorry for my English.
So kilonova are a little bit different. So kilonova are where you have a neutron star collision. I think they're going to be talking about that in the next Astronomy on Tap next month. But for a hypernova, I think if I've got this right, it's when you have an exceptionally massive star undergoing a core collapse. So it's stars bigger than, say, 40 to 50, even 60 times the mass of the sun. And so there's some kind of theory that there's a class of supernovae that I've actually done a lot of work on called Superluminous Supernovae. And these are exceptionally bright transients where you have peak luminosities 10 times the brightness of a type 1a supernova, and they decline much, much more slowly. And it's thought that some of these could be hypernovae, where you've got exceptionally massive stars undergoing core collapse. So you basically take a core collapse scenario, but you scale it up so it's massive.
Thank you. And we have another question, which is, what is the brightness of different brightness scales on the graph?
Yes.
I guess we're talking about this one?
Yeah.
Okay, so astronomers are awful. Observational astronomers like myself are really awful. We like to use a system called magnitudes. Okay, I've got to try and put this in context. Sorry, I'm always really bad at doing this. So a magnitude it's a logarithmic scale. So if you are one magnitude brighter, it's a logarithmic scale, but times 2.5. So if you're one magnitude brighter, you are 2.5 times brighter than the object that you are one magnitude brighter than. And if you are 2 magnitudes brighter, you are 2.5 squared, 2.5 times log. Oh man, I can't do maths. Sorry.
That's okay. I think generally just the more negative the number, the brighter it is,
yes,
right?
That's a better way of putting it. Thank you.
So on that scale,
the more negative a number, because it's an absolute brightness, so the more negative it is, the brighter your transient or your object is.
But maybe what will help is that can you maybe provide how something from this scale would look like in the sky?
Oh, okay.
On which kind of distance,
okay, so the
something like that. I think something like that would help. That at least will help me, because I also don't know.
Okay. Okay. So some of the brightest stars I think you can see with the naked eye have an absolute magnitude of, I think, -6, -7, perhaps, off the top of my head. So these would be the brightest stars that you see in the night sky. So anything so we don't naturally, I can never remember what the absolute brightness of the sun is, but these things are intrinsically brighter than the brightest stars that you see in the night sky, but we don't typically see them because we don't see them as this bright because they are further away from us. So this is how, if it was right up in front of your face, this is how bright these events would be. So not only would a type 1a there's many things a type 1a supernova would do to you if it was right up in front of your face, but it would very definitely blind you.
Yes.
Okay, so we also have some other questions, and yeah. So the question is also from Sapna Phat. Hope I pronounced it right. So yeah, how massive is the most massive star / black hole you have observed yet?
Okay, so in terms of massive stars, we've actually seen some stars that haven't quite collapsed yet. They're probably they are candidates for extremely bright stellar explosions that we've seen in the Large Magellanic Cloud. So the Large Magellanic Cloud is a satellite galaxy to the Milky Way, and it's host to lots of these star-forming regions, which Michael talked a little bit about earlier. And in these really massive star-forming regions, you've got clusters of really, really young stars, and we've measured stars by looking at the kind of there's all different ways of measuring the mass of a star. Some of that is you can do it through binary systems, but you can also do it through fitting different models. We found stars that are around 300 times the mass of the sun. I think the famous one is R136A1.
Jeez.
But in terms of black holes, if we're talking stellar mass black holes, so black holes that are probably formed through stars, I think the most massive we measured through the gravitational waves is about 80 solar masses. I'm probably wrong, and I'm hoping that people might correct. I think that might be a topic that comes up at the next Astronomy on Tap.
That's neat.
Yeah, and you have so far at least the last question is, yeah, what is your favorite type of transit event?
Oh,
Yeah,
yes.
personally.
Okay, it does change a little bit, because some days I'm like, oh, I don't really want to talk about that transient. So I hope you can see my mouse. So I'm a big fan of these things up here. They're called Superluminous Supernovae. I've done, this is basically one, and
Oh no.
basically stupidly luminous. So they're about 10 times brighter than a Type 1a supernovae, and they're extremely long-lived. And we think that some of these supernovae, it's not possible for we don't think it's possible for them to get as bright as they do through just nickel production alone to drive that main peak of the light curve. So we think that there's an additional source of energy that you have to input.
So I might stop you there, because my internet sort of glitched for a bit. You became a robot. Do you want to go back a little bit and repeat your explanation?
Okay, no worries.
So sorry.
Okay, so apologies if that all went robotic. So some of my favorite transients are these things here, which are called superluminous supernovae, which are really, really bright. They're about 10 times brighter than Type 1a supernovae, and their peak, we don't think that they can attain their peak luminosities through normal through the normal production of nickel, as you would in a core collapse supernova. We think you have to have an additional injection of energy in order to let them attain that peak brightness. And they're also really, really long-lived. They last for like hundreds and hundreds of days. So I have a very soft spot for those, but I haven't put them on this plot, which I'm really annoyed about. There was a really fast, really bright transient called AT2018 Cow that went off a couple of years ago. It got a lot of press attention, partly because of the name, but also because it basically just goes in terms of its light curve. It rises within like 3 days, it declines within like 20. No one can figure out what causes this transient. And I really like something that I can't figure out exactly what causes it. I think I just like a challenge. So yeah, some of those are my favorite transients.
That's super neat. I don't think we have...
Yeah, we don't have any more questions for now.
But Yogi, do you have any questions for Charlotte?
I mean, I study basically that, but from different perspective. And I guess if I start to ask questions, that's going to be for a while. But yeah, I study meteorites, and I study nickel, nucleosynthetic anomalies. I study this nickel produced in those supernovas, and trying to figure out in which exactly type of supernova it was produced. And yeah, so I guess I should not be asking questions right now.
That's fair.
That sounds really cool.
I guess I have one last question, which was, you were looking at the supernova curves, and I was wondering, because you see the supernovae once they're like bright, but on the plot you had like it rise up very quickly.
Yeah.
So like, have we managed to catch any supernova like before they got to their brightest?
Oh, I love you for asking this question. So it's actually the survey. So I'm working on a survey at the moment called the Young Supernova Experiment, and we are catching supernovae within a day or so of explosion. So I will flick back to.
Oh yeah, so it should be clarified, I guess, that the explosion isn't when it's at its brightest. The explosion actually happens before and it grows brighter.
Yeah, so the explosion actually happens somewhere down here, and it takes, for a type 1a supernova, it takes typically of order 18 to 20 days in the rest frame of the supernova for it to reach its peak luminosity. Because you basically have this expanding shell of burning material that's kind of moving outwards, and once it's at its maximum point, that's when the supernova is at its brightest. But there's a lot of research at the moment going into trying to find supernovae at the very beginning, so within a day or even hours of the point when they explode. And you do this by taking really, really high cadence survey images, so daily or even hourly survey images, in order to try and catch that point at which the supernova takes off.
Wow, that sounds very difficult. Okay, so we might wrap up the question time there and thank Charlotte again from your home, so you can clap. And maybe we'll also thank Michael again. Do we want to stop sharing and see everyone? There. Let me go into gallery view. So thank you for joining us on our first Astronomy on Tap online. I hope it went smoothly. And if we're lucky, we can go back to in person. We'll see. It's also totally fair if we can't. But let's thank Angus and Michael from home. And we hope that you enjoyed learning about stars from their birth to their boom. And hopefully we'll see you next month. So take care.
Again, thanks Reggie, thanks Georgi.
That's okay.
Yeah, thanks guys, that was awesome.
Bye. Bye.